This video is going to look at the laws of thermodynamics, which is kind of a formalization of a lot of the smaller things that we saw with temperature and heat and all of that, and how that comes into play when we deal with large collections of particles. So jumping into that, we want to talk about a couple of key terms or concepts just to make sure we're on the same page with these. So this is probably mostly review, but we're going to talk about it here. So thermal energy, so these first two terms both have to deal with energy. Thermal energy is the internal energy associated with the movement of the particles, or like the vibration of the particles. So this is basically what we talked about, where if something is at a higher temperature, its particles are moving faster. That's thermal energy, the measurement of that amount of energy. So just like we had said, temperature is roughly an average of kinetic energy. Thermal energy is that same sort of measurement, but for an entire object as opposed to averaging across all the particles. We'll talk more about this when we get into our calculation section, but just talking about this is the total amount of energy. And then heat is energy transfer as a result of different temperatures. So if two things have different temperatures, then the energy that moves between them is what we call heat. So temperature is, roughly speaking, the average measurement of the particles' kinetic energy. And then thermal equilibrium, which we've mentioned, but I don't know if we've explicitly defined. Thermal equilibrium is when two objects have the same temperature. That's going to be our basic definition. More in-depth, it has to do with this idea of the kinetic energies equalizing out. It actually has to do with the fact that no energy is transferred one way or the other overall, but in practice it means they're at the same temperature, so they're not moving heat back and forth. So we're going to talk about the laws of thermodynamics here, and this is just, like I said, a formalization of a bunch of stuff we've talked about. Nothing that we get into here should probably seem too crazy. It should kind of make sense from what we've talked about, but it's us putting that into kind of real clear language and terminology. So the zeroth law of thermodynamics, it's this long phrased out thing, but the simple English is going to make it nice and clear, but we want to give the full kind of formal definition here first. If two systems, so I've got an object, if you want to think about objects instead of systems, that might be easier for kind of start. Two objects or two systems, A and B, are in thermal equilibrium. With each other, and B is in thermal equilibrium with a third system, C, then A and C must also be in thermal equilibrium. Thermal equilibrium. So this is what allows us to actually define temperature. So like I said, thermal equilibrium is not technically speaking when things are at the same temperature, but for a practical working definition here, thermal equilibrium allows us to define temperature, and so because that's what we're more familiar with, that's why I've kind of explained that that's basically what's happening. So in simpler English, if A and B are the same temp, or the same temperature, and B and C are the same temperature, then A and C must be same temperature. Again, technically this is, to use that definition is kind of working backwards because we can only define temperature because of this law, so you can't really use it in the definition. But if you're just trying to understand what's the idea, it works perfectly fine. And the reason this allows us to define temperature, if you're wondering, is because it's saying that if I touch A and B together, they're not going to move heat between each other. Then B and C, when they touch, they're not moving heat. We can expect that A and C won't move heat. And that means there's something kind of uniform or the same about everything that's at the same thermal equilibrium. And that's where we actually define temperature, is everything that is the same temperature will be in thermal equilibrium with each other. So this lets us do something like make a thermometer that we say, oh, if I put this thermometer in boiling water and I mark where the mercury is or where the alcohol is, then we can say that's 100 degrees Celsius because we know that's the temperature water boils at. Then if I go touch it to something else and the thermometer goes to the same point, I know that must also be 100 degrees Celsius because the thermometer and the boiling water were in thermal equilibrium and they've reached a certain state, the alcohol being at a certain level. Then when the thermometer and, say, a hot piece of metal reached thermal equilibrium and they're in the same state, we know that that metal is as hot as the boiling water. Therefore, the metal must be 100 degrees Celsius. Okay, first law of thermodynamics is a little bit easier to kind of explain because we've talked about it before. The change in internal energy of a closed system equals the total heat that is added into the system, or the heat that flows into the system, minus the work done by the system. And so if you want to see this in equation terms, the change in the internal energy is equal to heat minus work. And this came up in the energy interaction model. And the main thing that's useful here is just that energy can be expressed both as heat and work. So if you heat up a gas, that gas can then do work and lose that energy that it got from heating it up. We're not going to do a whole lot with like the details of this, but if you continue studying physics or if you study some chemistry and you get into gases, there's a lot around this with kind of the interaction of heat and work here. Finally, the second law of thermodynamics is that the total entropy of a system remains the same or increases. In all spontaneous processes, it never decreases. Entropy roughly measures the organization of a collection of particles or of a system, and more precisely, it's the statistical likelihood of a given arrangement of particles. So what does this all mean? What do you need to know now? Well, entropy, the point here is with spontaneous processes. So if a process is going to happen without you forcing it to happen, so a chemical reaction or water evaporating, something that just kind of naturally happens without you doing something fancy to it, or without some external cause, the entropy must be staying the same or increasing. And what we're saying is basically entropy is talking about the statistical likelihood. We'll get more into this in a later lesson, but basically the idea is the reason that something is happening spontaneously is because the random movements of the particles is going to something that's more likely to exist. So sometimes you hear that as disorder because basically random arrangements that don't seem to have a structure are more likely to occur than ones that do seem to have a structure. So yeah, feel free to ask any questions or check in with anything you're not sure about, but that will wrap up kind of just a brief introduction here to the laws of thermodynamics.